It starts like this, a faint, flickering pulse drifting across the cosmos, picked up by a towering array of radio telescopes somewhere on Earth. The signal doesn't match any known cosmic phenomenon. It's too rhythmic, too precise, almost as if someone or something is trying to communicate. Scientists lean in, hearts racing, as the data scrolls across their screens. Could this be it, the moment humanity finally confirms we're not alone in the universe? This isn't science fiction, it's happened more times than you'd think. For decades, astronomers have been catching whispers from the void, signals so strange they defy easy explanation. Some vanish as suddenly as they appear, leaving behind only questions. Others repeat with eerie precision, like cosmic lighthouses blinking from billions of light years away. What are these mysterious transmissions, natural phenomena we don't yet understand? Or something far more extraordinary? Imagine staring into the night sky, knowing that hidden in the static between the stars are signals that could rewrite everything we know about the universe. Some of these cosmic messages are so bizarre they've sparked international headlines, debates among top scientists, and even classified government investigations. Take the famous WOW signal, a burst of radio waves so strong it was scribbled in red ink on a printout, circled with the exclamation that gave it its name. Decades later, we still don't know what caused it. Then there's the repeating fast radio bursts, blasts of energy so powerful they outshine entire galaxies for milliseconds before disappearing. And what about the strange, slow cycling signals that seem almost artificial? The more we listen, the more the universe feels less like a quiet wilderness and more like a crowded room, humming with voices we're only just beginning to hear. Today, we're diving deep into 25 of the most puzzling signals ever detected, each one a riddle wrapped in starlight. Some might be the cries of dying stars or the echoes of colliding black holes. Others, well, the possibilities are as vast as space itself. Together, we'll sift through the static, separate fact from speculation, and explore the leading theories that could explain these cosmic enigmas. Whether you're a skeptic or a true believer, one thing's certain: by the end of this journey, you'll never look at the night sky the same way again. So let's begin, because the universe is whispering and it's time we finally listened. One summer night in 1977, a radio telescope at Ohio State University picked up something extraordinary, a burst of radio waves so intense it lasted 72 seconds, blasting across the cosmos with a signal strength 30 times louder than the background noise of space. The astronomer who spotted it, Jerry Amon, was so stunned he circled the reading in red ink and scribbled "WOW" beside it, giving the signal its now famous name. What made it so remarkable wasn't just its power, it was the frequency. The signal hit exactly 1420 MHz, a quiet band where natural cosmic noise is minimal, almost as if whoever or whatever sent it knew this was the perfect channel to be heard. And then, just like that, it vanished, never repeating despite decades of searching. For years, scientists have wrestled with the puzzle. Could it have been a passing comet? In 2017, one team suggested hydrogen clouds from two comets might have reflected radio waves from Earth, mimicking an artificial signal. But critics pointed out those comets weren't even in the telescope's field of view when the WOW signal arrived. Others argue it might have been a rogue astrophysical event, a star collapsing, a black hole hiccuping, or some cosmic phenomenon we don't yet understand. But here's the haunting detail: the signal's narrow frequency range and precise structure don't match any known natural process. It's the kind of pattern you'd expect from a deliberate transmission. That leaves the most tantalizing and unsettling possibility. What if, for those 72 seconds, we weren't alone? Some researchers speculated could have been a beacon, a brief, intentional broadcast from a civilization thousands of light years away, flickering on just long enough to make us wonder. The truth, we may never know. The WOW signal remains one of the universe's most persistent riddles, a fleeting whisper that redefined our search for cosmic company. And if it was a hello from the stars, it's a reminder of how achingly vast space truly is, that even a shout as loud as WOW can disappear into the void before we have time to answer. The universe has a way of keeping astronomers on their toes. Just when we think we've seen it all, something comes along that shatters expectations. That's exactly what happened in 2012 when a team at the Arecibo Observatory in Puerto Rico caught something unprecedented. A fast radio burst that didn't just flash once and vanish, it kept coming back. Named FRB 121102, this was the first repeating fast radio burst ever discovered, and it flipped the script on everything scientists thought they knew about these cosmic mysteries. Most fast radio bursts are like cosmic fireworks, brilliant, one-off explosions of energy that last mere milliseconds. But this one, it pulsed again and again, sometimes months apart, sometimes in rapid succession, as if something or someone was hitting a cosmic reset button. Even more intriguing was its home, a tiny, unassuming dwarf galaxy 3 billion light-years away, a place where stars form at a frantic pace. Why there? What could possibly be generating such powerful, repeating signals in a galaxy so small? The leading theory points to magnetars, super-dense, highly magnetized neutron stars spinning like cosmic tops. When their crusts crack under immense pressure, they can unleash bursts of energy powerful enough to outshine entire galaxies. Some scientists think FRB 121102 might be a magnetar in overdrive, its magnetic field so intense it periodically rips itself apart, sending shockwaves across the universe. But here's the catch: even magnetars shouldn't repeat this predictably. There's no known natural process that neatly explains the timing and structure of these bursts. That's where things get speculative and thrilling. A handful of researchers have dared to ask, could this be something else entirely? The bursts are so precise, so structured, that some have floated the idea of an artificial origin. Picture a super-advanced civilization harnessing the energy of stars, perhaps using planet-sized transmitters to send pulses across galaxies. It's a long shot, but when nature doesn't provide answers, science has to consider every possibility. For now, FRB 121102 remains a tantalizing enigma, a signal that refuses to be ignored. Whether it's the death throes of a magnetar or something far more extraordinary, one thing's clear: the universe still has secrets we're only beginning to uncover. And with every repeating burst, the mystery only deepens. In 2003, astronomers scanning the skies for signs of extraterrestrial intelligence stumbled upon something baffling. A signal so strange it earned the clunky but tantalizing name SETI-02+14a. Picked up 3 times by the SETI at Home project, which uses idle computers worldwide to analyze radio telescope data, this signal stood out immediately. Unlike the background hum of the cosmos, SETI-02+14 pulsed at a frequency of about 1420 MHz, the same quiet band as the WOW signal, a range many scientists consider ideal for interstellar communication. But here's where it gets weird: the signal appeared to drift. Its frequency shifted slightly over time, as if the source was moving fast. Most natural cosmic radio sources don't behave this way. Pulsars and quasars emit steady, predictable frequencies. SETI-02+14a, however, seemed to dance, its origin point hovering near a patch of empty space in the constellation Pisces, where no known stars or planets exist. That left researchers scratching their heads. What could possibly be generating a signal this peculiar in the middle of cosmic nowhere? Some proposed it might be a highly unusual pulsar, one with a wobble so extreme it mimicked artificial movement. Others suggested equipment glitches or interference from Earth-based sources, perhaps a passing satellite or a microwave oven left running near an observatory. But none of those explanations fully fit. Then came the elephant in the room, the possibility of extraterrestrial technology. The signal's drifting frequency matched what you'd expect from a transmitter on a rapidly rotating planet, one orbiting a star so distant we can't even see it. Imagine a civilization far more advanced than ours, broadcasting from a world spinning so fast its signals stretch and compress like a cosmic Doppler effect. It's a thrilling idea, but here's the catch: SETI-02 plus 14 vanished before scientists could pin it down. Despite repeated attempts, it hasn't been detected since, leaving us with more questions than answers. Was it a technical hiccup, a bizarre astrophysical fluke, or just maybe the fleeting fingerprint of intelligence beyond Earth? The truth is, we'll never know for sure unless the signal returns. But that's the beauty and frustration of the cosmic hunt. The universe loves a good mystery, and SETI-02 plus 14 remains one of its most elusive. Before fast radio bursts became one of astronomy's greatest puzzles, there was the one that started it all: the Lorimer burst, detected in 2007 but hidden in archival data from 2001. This brief, blazing signal lasted just 5 milliseconds, yet packed more energy than the sun emits in a month. It wasn't just powerful, it was baffling. The burst seemed to come from nowhere, a cosmic flashbulb popping in the darkness and then vanishing without a trace. For years, astronomers debated whether it was even real. Could it have been a glitch, an instrument malfunction, or something far more profound? The data didn't lie. The signal's dispersion, how its waves stretched out as they traveled through space, pointed to an origin billions of light-years away, far beyond our galaxy. That ruled out earthly interference, but what could produce such a short, intense burst of radio waves? The usual suspects: supernova, neutron stars, even black hole collisions didn't fit. Those events release energy over hours or days, not milliseconds. The Lorimer burst defied every textbook explanation, leaving scientists with a tantalizing riddle and a nagging question. Was this a fluke or the first glimpse of something entirely new? It took nearly a decade for the astronomy community to accept the reality of fast radio bursts. Skepticism lingered, partly because no one could find another like it. That changed when the Arecibo telescope caught a repeating burst in 2012. Proving these weren't one-off glitches but a genuine cosmic phenomenon. Suddenly, the Lorimer burst wasn't just an anomaly, it was the Rosetta Stone of a whole new field of study. Today, we know fast radio bursts are common, with hundreds detected since that first mysterious blip. Some come from magnetars, others from colliding neutron stars, but the Lorimer burst remains special, the spark that lit the fire. Its brevity and power still challenge our understanding of the universe, a reminder that sometimes the biggest discoveries begin with the smallest, most fleeting signals. And who knows, the next burst might be the one that finally cracks the code. In December 2020, astronomers with the Breakthrough Listen project detected something extraordinary: a narrowband radio signal beaming from the direction of Proxima Centauri, the closest star to our solar system. Dubbed BLC-1, this signal sent shockwaves through the scientific community. Here was a transmission that ticked all the boxes for a potential technosignature. It was concentrated at 982 MHz, a frequency typically free of natural cosmic noise, and it drifted slightly as if coming from a planet in motion. Even more tantalizing was its origin. Proxima Centauri hosts at least 2 planets, one of which orbits within the star's habitable zone, a place where liquid water and perhaps life could exist. Could this be humanity's first encounter with an alien civilization just 4.2 light-years away? The initial observation stirred a mix of excitement and skepticism. Unlike other cosmic signals, BLC-1 appeared only once during multiple scans, suggesting it wasn't a repeating astrophysical event. Its frequency also aligned suspiciously close to known human-made radio interference surface radar, satellites, or even everyday electronics. But the clincher came when researchers dug deeper. the signal's drift rate, the way its frequency shifted, didn't quite match the expected motion of Proxima Centauri's planets. Instead, it bore an uncanny resemblance to the wobble of Earth-based transmitters, likely caused by a passing aircraft or a malfunctioning device near the observatory. By 2021, the Breakthrough Listen team reached a sobering conclusion. BLC-1 was almost certainly human-made, but the story doesn't end there. This near miss taught scientists a valuable lesson about the hunt for extraterrestrial intelligence. The universe is full of radio noise, some natural, some manufactured, and distinguishing the two requires painstaking effort. Even so, Proxima Centauri remains a prime target. Its planets are among our best candidates for harboring life, and future telescopes may yet uncover signals that can't be explained away. BLC-1 might have been a false alarm, but it's a reminder that the next real detection could come from the unlikeliest of places, even our cosmic backyard. Sometimes the most profound discoveries in science begin with a moment of pure bewilderment. That's exactly what happened in 1967, when Cambridge astrophysicist Jocelyn Bell Burnell noticed something peculiar in her radio telescope data, a series of rapid, rhythmic pulses arriving every 1.337 seconds with such clockwork precision it seemed impossible to be natural. The signal, dubbed CP1919 for its celestial coordinates, defied all expectations. Here was a cosmic metronome ticking across the void with unnatural consistency. The team's first thought they'd stumbled upon a beacon. The pulses were so regular, so artificial seeming, that Burnell and her advisor Anthony Hewish privately nicknamed them LGM signals, short for Little Green Men. For a brief, electrifying moment, the possibility hung in the air. Had humanity just intercepted an alien broadcast, the idea wasn't as far-fetched as it sounds. At the time, scientists speculated that an advanced civilization might use pulsed radio signals as cosmic lighthouses, a way to announce their presence across the galaxy. The team even kept the discovery secret for months, wary of sparking public hysteria until they could rule out extraterrestrial origins. But as more of these strange signals were detected across the sky, the truth became clear: they weren't hearing from aliens. They'd discovered something equally extraordinary: pulsars, the rapidly spinning corpses of massive stars. These cosmic powerhouses are neutron stars, objects so dense a teaspoon of their material would weigh billions of tons. As they rotate, beams of radiation shoot from their magnetic poles like interstellar searchlights, sweeping past Earth with each spin to create those eerily precise pulses. Far from being alien engineering, pulsars turned out to be nature's most precise clocks, some so stable they rival atomic timekeepers on Earth. But the LGM episode wasn't just a humorous false alarm. It reshaped our understanding of stellar evolution, proving that the deaths of massive stars could leave behind these bizarre, ultra-dense remnants. The discovery also highlighted a crucial lesson in the search for extraterrestrial intelligence. Sometimes the universe delights in mimicking the very signals we hope to find. Pulsars, with their unnatural-seeming regularity, became the gold standard for distinguishing natural phenomena from potential technosignatures. And while Burnell and her team didn't find little green men that day, they unlocked one of the universe's most captivating mysteries, a reminder that even in moments of mistaken identity, science can stumble upon truths far stranger than fiction. Of all the strange signals echoing across the cosmos, few have baffled scientists quite like FRB 180916, a fast radio burst that doesn't just repeat, but does so with a precision that feels almost theatrical. Discovered in 2019 by the CHIME telescope in Canada, this burst cycles like clockwork, active for 4 days, silent for 12, then back again, completing its eerie 16-day rhythm without fail. It's the first FRB ever found with a predictable schedule, and that regularity has sent theorists spiraling. What kind of cosmic phenomenon could possibly keep time so meticulously? The signal's home only deepens the intrigue. Unlike many FRBs that originate in chaotic dwarf galaxies, this one stems from a calm, spiral galaxy 500 million light-years away, a place with orderly arms of stars, not the turbulent stellar nurseries typically linked to explosive astrophysical events. If extreme environments like magnetars usually power these bursts, why is this one so well behaved? One leading theory suggests an elaborate cosmic dance. A neutron star locked in orbit with a massive companion, perhaps a black hole or a luminous star. As the neutron star swings around its partner, its powerful magnetic field might periodically align with our line of sight, beaming energy toward Earth like a lighthouse flashing on a schedule. The 16-day cycle could mirror the time it takes to complete one full orbit, but not everyone's convinced. Some researchers point out that even this elegant model doesn't fully explain the burst-sharp 4-day on window or the uncanny consistency of its timing. Could there be something even stranger at play? A handful of speculative papers have dared to explore more exotic explanations, like artificial megastructures. Imagine a civilization advanced enough to harness the energy of stars, constructing colossal transmitters that sweep their beams across the galaxy in deliberate patterns. While there's zero concrete evidence to support this, the sheer precision of FRB 180916 forces science to confront an unsettling truth. Nature rarely produces rhythms this exact without a reason. For now, the 16-day repeater remains an enigma wrapped in a spiral galaxy. Every new detection adds a piece to the puzzle, but the full picture still eludes us. Whether it's a celestial waltz of stars or something beyond our current understanding, one thing's certain: this isn't just another cosmic blip. It's a signal that demands we rethink what's possible in the universe, and that's what makes it unforgettable. In 2016, a star named HD 164595 suddenly became the center of attention for astronomers around the world. Located 94 light-years away in the constellation Hercules, this sun-like star emitted a radio signal so peculiar it sent ripples through the scientific community. Detected by the Ratan 600 radio telescope in Russia, the signal clocked in at 11 GHz, a frequency often used for satellite communications and radar here on Earth. What made it extraordinary wasn't just its strength, but its origin. HD 164595 wasn't just any star. It was known to host at least one Neptune-sized planet, raising the tantalizing question: could this be a transmission from an advanced civilization? For a brief, electrifying moment, the pieces seemed to fit. The signal's narrow bandwidth and artificial-seeming structure aligned with what scientists had long predicted an intentional interstellar message might look like. Researchers even crunched the numbers on how much energy would be required to send such a signal across interstellar space. The results were staggering. If aimed deliberately at Earth, it would demand power equivalent to harnessing the entire energy output of a Kardashev Type II civilization, one capable of harnessing the total energy of its star. The implications were dizzying. Had we just stumbled upon evidence of a society far more advanced than our own? But the excitement was short-lived. Almost as quickly as the signal appeared, skepticism set in. Astronomers pointed out that 11 GHz is a notoriously noisy frequency cluttered with human-made interference from military radar, satellites, and even microwave ovens. When other telescopes, including the SETI Institute's Allen Telescope Array, tried to confirm the detection, they heard nothing but silence, no repeat signal. No corroborating data. The more scientists scrutinized it, the more likely it seemed that HD 164595's message was just a case of cosmic confusion, a stray human signal masquerading as something alien. Yet the story doesn't end with simple dismissal. The episode underscored a growing challenge in the search for extraterrestrial intelligence. Our own technological noise is increasingly polluting the cosmic radio spectrum. As Earth buzzes with more satellites, wireless devices, and radar systems, distinguishing between a genuine alien broadcast and terrestrial interference becomes exponentially harder. HD 164595 signal may have been a false alarm, but it served as a crucial reminder. The universe is vast, but our own backyard is full of static. And if we ever do hear a real message from the stars, cutting through that noise will be the ultimate test. In 2019, astronomers scanning the sky with the Australian Square Kilometre Array Pathfinder stumbled upon something completely unexpected: enormous, faint rings of radio emission floating in space like cosmic smoke signals. These weren't just any celestial objects, they were named odd radio circles, or ORC, precisely because no one could figure out what they were. Each one spans hundreds of thousands of light years across, dwarfing entire galaxies, yet they emit nothing but radio waves, remaining invisible to optical, infrared, and X-ray telescopes. The moment researchers spotted them, the race was on to explain these ghostly giants. Were they the aftermath of a cataclysmic explosion, the echoes of a long-dead quasar, or something even stranger? One leading theory suggests ORCs might be shockwaves from colossal events in galactic history, like two supermassive black holes merging at the heart of a galaxy, sending ripples through intergalactic gas. Imagine tossing a stone into a pond, but on a scale so vast the ripples would take millions of years to cross. Another idea points to starburst galaxies, where frenzied star formation unleashes torrents of energy, potentially blowing bubbles of radio emission into space. But there's a catch: most ORCs don't seem to have a visible galaxy at their center, leaving scientists puzzled about what could have triggered such titanic waves. Then there's the more exotic possibility: ORCs could be relics of an ancient universe-shaking event. Some researchers speculate they're the remnants of a supernova squared, an explosion so powerful it makes regular supernova look like firecrackers. Picture a hypergiant star collapsing not just into a neutron star or black hole, but detonating with enough force to rip a hole in the surrounding space, leaving behind a radio wave echo that lingers for eons. Others have even floated the idea of intergalactic lightning, a vast electrical discharges arcing between galaxies, though there's little evidence to support such a dramatic phenomenon. But the mystery deepens when you consider the ORC's perfect circularity. Cosmic explosions tend to be messy, leaving irregular debris fields. These structures, by contrast, are unnervingly symmetrical, as if shaped by some invisible force. A handful of theorists have dared to ask whether we're seeing the imprint of advanced technology, a Dyson sphere gone rogue, perhaps, or the remnants of a civilization harnessing energy on a galactic scale. It's a wild thought, but in the absence of natural explanations, even the improbable deserves a glance. For now, ORCs remain one of astronomy's most tantalizing puzzles. Every new observation peels back another layer, revealing more questions than answers. Whether they're the aftermath of an unseen cosmic catastrophe or something beyond our current physics, one thing's clear: the universe still holds wonders we're only beginning to uncover. And with each strange radio circle we map, the cosmos reminds us just how much we have left to learn. If fast radio bursts are the universe's way of keeping astronomers guessing, then FRB 190520 is its most mischievous puzzle yet. Discovered in 2019 by China's 500-meter aperture spherical telescope, this signal doesn't just repeat, it practically never stops. Unlike most FRBs that flash briefly and vanish, this one fires off bursts almost daily, earning it the nickname the persistent repeater. But that's not even the strangest part. When researchers pinpointed its location to a small, ancient dwarf galaxy 3 billion light-years away, they found something utterly unexpected: a swirling cloud of plasma surrounding the source, drifting through space like a cosmic fog. This dense, magnetized shroud is unlike anything seen near other FRBs. Normally, these bursts travel through relatively clean intergalactic space, but FRB 190520 signals have to fight through this turbulent cloud, distorting their waves in ways that reveal its presence. The leading theory: we might be witnessing the fiery adolescence of a newborn magnetar, a super-dense neutron star with a magnetic field so intense it could strip data from a credit card 1,000 light-years away. When these cosmic powerhouses are young, they're thought to be surrounded by debris from the star that birthed them, material that hasn't yet been blasted away by the magnetar's furious energy. That could explain the persistent bursts and the lingering plasma cloud. Yet even this explanation leaves gaps. Why does this magnetar, if that's what it is, behave so differently from others? Most magnetars flare unpredictably, but FRB 190520 pulses with a stubborn regularity that defies expectations. Some researchers speculate we might be seeing two phenomena at once: a magnetar embedded within an especially dense stellar nursery, its environment amplifying and sculpting the bursts in ways we don't yet understand. Others go further, suggesting the plasma cloud could be artificial, a deliberate construct designed to focus or modulate the signal. Imagine an advanced civilization building a cosmic lighthouse, using a magnetar as its power source and surrounding it with an engineered shell to steer its energy across the galaxy. It's a wild idea, but that's what makes FRB 190520 so compelling. It challenges every assumption we have about these enigmatic signals. Whether it's a celestial toddler throwing tantrums or something far more profound, one thing's clear: the universe still has a flair for the dramatic. And as long as this persistent repeater keeps broadcasting, scientists will keep listening, knowing that the most ordinary seeming bursts might just rewrite the rules of astrophysics. Of all the stars that have captured astronomers' imaginations, few have sparked as much intrigue as KIC 8462852, better known as Tabby's star. Nestled in the constellation Cygnus, 1,500 light-years away, this unassuming flicker of light became famous in 2015 when citizen scientists noticed something extraordinary. Its brightness dipped by up to 22% in irregular, dramatic plunges, far more than any known planet could explain. But just when scientists thought the mystery couldn't get stranger, in 2017, radio telescopes picked up another tantalizing clue: fleeting signals that seemed to pulse from the same patch of sky. The radio bursts detected by the Green Bank Telescope in West Virginia were subtle, nothing like the powerful blasts of fast radio bursts. Instead, they flickered weakly at specific frequencies, almost as if someone was fine-tuning a cosmic radio dial. What made them remarkable was their timing. They coincided with periods when Tabby's star's light was dimming most severely. Could there be a connection? Some researchers speculated the signals might be tied to the star's bizarre behavior. One theory suggested swarms of comets breaking apart, their icy debris reflecting radio waves as they vaporized near the star. Others pointed to intense stellar activity, sunspots or flares magnified by clouds of circumstellar dust. But then there's the hypothesis that refuses to fade, the megastructure idea. Back when Tabby's star's dimming was first discovered, astronomer Jason Wright famously proposed that its irregular light patterns could hint at an alien megastructure, like a Dyson swarm, a vast array of energy-harvesting satellites built by an advanced civilization. The radio signals, faint as they were, added fuel to the fire. Could they be leakage from immense power transmission, or even communication between these hypothetical constructs? The frequencies detected, around 6 to 10 GHz, overlap with those used for radar and satellite tech here on Earth, making the parallels hard to ignore. Yet skepticism runs deep. When follow-up observations failed to replicate the signals, doubt crept in. Was it just interference from passing satellites or Earth-based equipment? Even the star's dimming has alternative explanations. Massive dust clouds or remnants of a devoured planet could mimic the same erratic light patterns. Still, the allure of the unknown lingers. Tabby's star remains a cosmic Rorschach test. What you see in its flickers and whispers depends on what you're willing to believe. For now, the radio signals are just another layer in one of astronomy's most enduring puzzles. Whether they're the murmurs of a dying star, the crackle of drifting comets, or just maybe the hum of something far more extraordinary, one truth remains: Tabby's star isn't done surprising us. And until we find definitive answers, it stands as a reminder that sometimes the most ordinary-looking stars hide the wildest secrets. In the world of cosmic mysteries, few mix-ups are as delightfully absurd as the case of the Puritan's radio signals that had astronomers scratching their heads for years before revealing their hilariously terrestrial origins. These bursts, first detected at Australia's Parkes Observatory in the late 1990s, seemed at first glance to be distant cousins of fast radio bursts, short, intense pulses of radio waves arriving from the depths of space. But there was something off about them. Unlike FRBs, which scatter their signal across frequencies as they travel through the cosmos, Puritans stayed eerily focused, as if someone had aimed a radio flashlight directly at Earth. For over a decade, the signals defied explanation. Some researchers speculated they might be atmospheric phenomena, lightning on steroids, or high-energy particles slamming into Earth's upper atmosphere. Others wondered if they were artifacts of the telescopes themselves, glitches in the machinery. Then, in 2015, a breakthrough came from the unlikeliest of places, the observatory's kitchen. An intern noticed something peculiar every time someone opened the door of the microwave oven mid-cycle. The telescope picked up a burst of radio waves almost identical to the mysterious Puritans. The culprit, a 2.4 GHz magnetron, the same technology that powers household microwaves leaking radiation when interrupted. The revelation was equal parts embarrassing and enlightening. Those cosmic signals, they'd been coming from astronomers reheating their lunches, but the comedy of errors had a silver lining. The incident forced observatories worldwide to tighten their detection protocols, implementing stricter filters to weed out human-made interference. Suddenly, signals that might have been dismissed as Puritans had to pass a new litmus test. Could they be replicated by slamming a microwave door? What started as a cosmic wild goose chase ended up sharpening the tools of the trade. Today, Puritans serve as a cautionary tale, a reminder that the universe's greatest mysteries sometimes turn out to be hilariously close to home. And for every genuine signal from the void, there's a chance it's just someone's forgotten burrito. Deep in the constellation Vulpecula, the little fox lies a star that once sent the astronomy world into a frenzy. Known by its unassuming catalog number TYC 3162911, this ordinary-looking sun was the source of a radio signal so peculiar that for a time it stood as one of the strongest candidates for an alien megastructure ever discovered. The story begins in 2015, when the Allen Telescope Array in California picked up an unusual spike in radio waves coming from the star's direction. Unlike the chaotic noise of most cosmic radio sources, this signal was narrowband, focused on a tight range of frequencies, the kind of precision often associated with artificial transmissions. The timing couldn't have been more electrifying. Just months earlier, astronomers had noted that TYC 3162911 exhibited bizarre dimming patterns, its light dipping erratically by up to 20%, far too extreme to be caused by orbiting planets. Some researchers, including Penn State's Jason Wright, floated an astonishing explanation. What if we were seeing the shadows of a Dyson swarm, a vast constellation of energy-harvesting satellites built by an advanced civilization? The radio signal seemed to fit the narrative perfectly. If a society had built such a megastructure, wouldn't they also be transmitting? But science thrives on skepticism. As telescopes around the world trained their dishes on Vulpecula, alternative explanations emerged. The signal, it turned out, had a mundane but fascinating origin: a passing comet. Observations revealed a massive cloud of icy debris orbiting the star, likely left behind by a disintegrating comet or colliding asteroids. As this material vaporized, it could have scattered radio waves in a way that mimicked an artificial broadcast. The star's erratic dimming, swarms of dust from the same debris drifting unpredictably between the star and Earth. Yet even with these natural explanations, a sliver of doubt lingers. The original radio signal's narrowband nature still doesn't perfectly align with typical cometary activity. And while dust clouds explain the dimming, they can't account for every anomaly in the star's behavior. Could there still be room, even a tiny one, for something more extraordinary? Most scientists agree the answer is probably no, but Vulpecula's star remains a cautionary tale in the search for extraterrestrial intelligence. Sometimes the universe teases us with possibilities just strange enough to keep us guessing, and in that uncertainty lies the thrill of the cosmic hunt. FRB 202000120E wasn't just another fast radio burst, it was a cosmic rule breaker. When astronomers pinpointed its origin in 2021, the discovery sent shockwaves through astrophysics. Unlike most FRBs that hail from galaxies billions of light-years away, this one erupted from a place shockingly close to home, a star cluster 40,000 light-years distant, nestled right inside our own Milky Way. That proximity made it the first galactic FRB ever detected, and it turned everything scientists thought they knew about these bursts upside down. Here's why this matters. Before FRB 202000120E, the leading theory suggested fast radio bursts were tied to magnetars. Super-dense, highly magnetized neutron stars, but only those in extreme, distant environments like turbulent dwarf galaxies. This signal, however, came from a globular cluster, a serene retirement home for ancient stars where magnetars weren't even supposed to exist. The discovery forced a radical rethink. If magnetars could form in such quiet neighborhoods, their birth might not require the violent stellar explosions we assumed. The plot thickened when researchers traced the burst to a specific object, a magnetar named SGR 1935+2154. Unlike its distant cousins, this one wasn't just a one-time offender. It fired off multiple bursts, some weaker, some stronger, providing an unprecedented close-up of magnetar tantrums in action. The data revealed something peculiar. The burst structure mirrored those from FRB's billions of light-years away, suggesting the same physics might be at play across the universe, regardless of environment. Yet questions lingered. Why was this magnetar so active in a place where stars are typically old and calm? One theory points to a cosmic collision, perhaps two white dwarfs smashed together, creating a magnetar where none should be. Another idea suggests the magnetar might be a blitzar, a neutron star born so massive its core briefly resisted collapsing into a black hole, unleashing energy in sporadic explosions. Whatever the truth, FRB 202000120E did more than defy expectations. It handed scientists a lab in our galactic backyard to test theories that had once been pure speculation. The implications ripple far beyond this one signal. If magnetars can form in unexpected places, the universe might be peppered with far more FRB sources than we imagined. And if a single magnetar in our galaxy can mimic the most distant bursts, it hints that the cosmos might be simpler and stranger than we ever dreamed. What once seemed like exotic fireworks from the edge of reality might just be the universe's way of showing us how much we still have to learn. Imagine the universe as a vast, tranquil lake, every galaxy, every star drifting gently with the current of cosmic expansion. But in the early 2000s, astronomers noticed something unsettling. Entire clusters of galaxies, thousands of them, were moving in unison as if caught in some invisible river current. Not expanding with the universe, but pulled sideways toward a single patch of space beyond the edge of everything we can observe. They called it the dark flow. And to this day, no one knows what's tugging at them. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light revealed something impossible. Galaxy clusters racing at over 2 million miles per hour toward a point in the sky near the constellations Centaurus and Vela. At first, scientists assumed it was an error. The observable universe is, by definition, everything we can see. There shouldn't be anything massive enough outside to exert such a pull. But the data held up. Whatever this force was, it defied the laws of physics as we know them. One theory suggests the dark flow could be evidence of a parallel universe, a neighboring bubble of space-time brushing against our own, its gravitational influence leaking across the cosmic boundary. Picture two soap bubbles pressed together. Where they meet, matter on one side might feel the tug of the other. It's a radical idea, but not impossible in certain versions of string theory. Others propose a quantum anomaly, a flaw in the fabric of reality where the rules of gravity behave differently, warping space-time on a scale we've never seen. Then there's the unsettling alternative that our universe isn't as observable as we thought. The dark flow's direction points toward a region obscured by the Milky Way's dust, a cosmic blind spot. Could there be a superstructure there, a colossal mass we've missed? Some researchers speculate about a great attractor, a concentration of dark matter so vast it bends the motion of galaxies around it. But even that doesn't fully explain the sheer scale and uniformity of the dark flow. What makes this mystery so haunting is its implications. If the dark flow is real, it means there's something out there, something beyond our cosmic horizon, beyond the reach of light itself, reshaping the universe in ways we can't yet comprehend. Whether it's a ghost from another dimension, a crack in the laws of physics, or something entirely unforeseen, one thing's certain: the cosmos still has secrets that defy even our boldest theories. And somewhere in the darkness between the stars, the universe is still moving in ways we don't understand. NGC 6946, nicknamed the Fireworks Galaxy for its frequent supernova, should have been predictable. A place where massive stars live fast, die young, and go out with a spectacular bang. But in 2019, astronomers witnessed something that defied every expectation. A luminous blue variable star, 25 times more massive than our Sun, simply disappeared. No explosion, no blinding flash, just a star that had shone brightly for millions of years, vanishing as if someone had flipped a cosmic light switch. Then came the X-rays, a strange, fluctuating signals pulsing from the same spot where the star had been. The mystery only deepened when researchers realized this wasn't an isolated event. Over decades, multiple stars in NGC 6946 had vanished without a trace, each time followed by the same eerie X-ray afterglow. The leading theories scrambled to explain how a star could bypass death by supernova. One possibility involves a failed explosion, a scenario where a star's core collapses directly into a black hole, swallowing the entire star from the inside out before it can erupt. Imagine a dying campfire collapsing into a sinkhole, its light snuffed out before the final sparks can fly. The X-rays could then be the death throes of matter spiraling into the newborn black hole, a last whisper before being silenced forever. But there's a problem. Even failed supernova should leave some trace, a neutrino burst or infrared glow, and NGC 6946's vanishing acts leave nothing behind but those enigmatic X-rays. This absence of evidence has fueled more speculative ideas. Could advanced civilizations be at work? The notion isn't as far-fetched as it sounds. A Kardashev Type 2 civilization, one capable of harnessing the energy of its star, might dismantle stars piece by piece, converting their mass into usable power through hypothetical megastructures like Dyson spheres. The X-ray signatures could be waste heat from such an operation, or even deliberate beacons signaling their presence. Skeptics counter that natural explanations, no matter how elusive, are always more probable than alien engineering. Yet the sheer number of missing stars in this galaxy raises an uncomfortable question. Why here? Why so many? The fireworks galaxy's X-ray mystery lingers like a cosmic whodunit, challenging our understanding of stellar life cycles. Whether it's a previously unknown form of stellar death or something beyond our current physics, one truth is undeniable. Sometimes the universe's most profound puzzles aren't about what's there, but what isn't. And in the silence where stars should have died, we're left listening for answers that haven't yet arrived. Deep in the infrared spectrum, where human eyes can't see and most telescopes rarely look, the universe hides some of its strangest secrets. Among them are the so-called unidentified infrared emissions, mysterious bands of light radiating from distant galaxies that defy every conventional explanation. These aren't the warm glows of stars or the predictable heat signatures of cosmic dust. They're something else entirely, sharp, unexplained spikes at specific wavelengths, as if the cosmos itself had flipped on a series of invisible neon signs. At first, astronomers assumed they were seeing ordinary polycyclic aromatic hydrocarbons molecules found in everything from car exhaust to interstellar dust clouds. But the emissions didn't match. Their wavelengths were all wrong, their intensities too consistent across wildly different galactic environments. Some researchers proposed exotic quantum phenomena, like tiny carbon crystals forming in space under conditions we've never replicated on Earth. These nanocrystals, theoretically, could vibrate at just the right frequencies to produce the bizarre infrared signatures. It's a compelling idea, except no one's ever found direct evidence these crystals exist. That's where the theories take a turn toward the extraordinary. In the early 2000s, astrophysicists began floating a radical alternative. What if these emissions weren't natural at all? The signal's precision and uniformity raised an unsettling possibility: industrial activity on a galactic scale. Picture a civilization so advanced it's harnessed the energy of stars, converting waste heat into structured infrared patterns as a byproduct of massive energy collection. The concept isn't pure speculation. Here on Earth, our own infrared footprint from cities, factories, and even satellites bears an eerie resemblance to these cosmic signals, just billions of times smaller. Of course, skepticism runs deep. The scientific mantra, "extraordinary claims require extraordinary evidence," weighs heavily here. Critics argue that invoking alien megastructures is a last resort, a leap too far when natural explanations, however incomplete, still hold some ground. Yet the unidentified infrared emissions persist, unexplained, flickering across the cosmos like a fingerprint we can't quite match. Whether they're the whispers of quantum oddities or the exhaust fumes of distant civilizations, one thing's certain: they're a reminder that even in the invisible corners of the universe, the most ordinary-looking light can hide the most extraordinary secrets. Deep in the heart of our galaxy, near the swirling chaos of the Milky Way's center, astronomers stumbled upon something utterly bizarre, a signal that didn't just repeat but sang. Known as GCRTJ 1745-3009, this radio transient erupts every 77 minutes with a burst so peculiar it's been nicknamed the cosmic whistle. Imagine a celestial lighthouse, but instead of a steady pulse, it emits a rapid, rising chirp, like a tuning fork struck against the fabric of space-time itself. The whistle's origin remains one of radio astronomy's most stubborn puzzles. Most repeating cosmic signals come from spinning neutron stars or colliding black holes, but this one defies easy categorization. For starters, it's not where it's supposed to be. The galactic center is a crowded, violent place packed with supermassive black holes and magnetized gas clouds. Yet the cosmic whistle emerges from a relatively quiet patch, as if something hidden there is deliberately humming to itself. One leading theory points to a neutron star with a twist, not just any neutron star, but one entangled in a magnetic dance with an unseen companion. Picture a highly magnetized pulsar locked in orbit with another dense object, perhaps a white dwarf or even a rogue planet. As they circle each other, their interacting magnetic fields could twist into knots, periodically snapping and releasing bursts of energy in those distinctive rising tones. It's a cosmic version of a finger running along the rim of a wineglass, creating vibrations that ripple across the galaxy. Then there's the plasma physics angle. Some researchers speculate the whistle might be a natural radio laser, a phenomenon where clouds of magnetized plasma amplify radio waves into coherent beams. Under just the right conditions, think superheated gas threaded with magnetic fields. These plasma clouds could act like interstellar amplifiers, producing chirps as charged particles spiral along magnetic lines. The 77-minute cycle, that could be the time it takes for the plasma to recharge between bursts. But here's where it gets wild. A handful of scientists have entertained an even more exotic possibility. What if the whistle is artificial? Before you dismiss the idea, consider its precision. The signal's frequency sweeps upward with mathematical neatness, a pattern rarely seen in nature. Could it be some form of navigation beacon, or even a malfunctioning relic from a long-dead civilization? Most astronomers consider this far-fetched, but in a universe full of surprises, even the wildest ideas deserve a glance. For now, GCRTJ 1745-3009 keeps its secrets. Every 77 minutes, it sings its eerie tune into the void, a siren call from the galactic core. Whether it's the cry of a magnetized star, the hum of superheated plasma, or something beyond our current understanding, one thing's clear: the cosmos still has a flair for the unexpected. And somewhere in the static between the stars, the universe is still whistling a tune we're only beginning to hear. In the vast catalogue of cosmic radio bursts, few stand out like the one astronomers call the Dragonfly. Detected in 2018 by the Canadian Hydrogen Intensity Mapping Experiment, this signal lasted a mere millisecond, yet in that blink of an eye, it unleashed more energy than our Sun emits in 3 days. What made the Dragonfly burst extraordinary wasn't just its power, but its singularity. Unlike repeating fast radio bursts, this was a one-off event, a cosmic scream that echoed once and then vanished into silence. The mystery deepens when you consider its origins. Tracing its path through intergalactic space, scientists pinpointed the Dragonfly's source to a region devoid of any known galaxies, a cosmic no-man's land where such energetic events shouldn't occur. No star clusters, no black hole mergers, not even a faint dwarf galaxy, just empty space. That left researchers grappling with a fundamental question: what could possibly generate a burst this powerful in the middle of nothing? One daring theory points to the edges of known physics. Some physicists speculate the Dragonfly might be the death cry of a microscopic black hole, one so small it defies classical astrophysics. According to quantum theory, black holes aren't entirely black. Over unimaginable timescales, they evaporate, leaking particles in a process called Hawking radiation. But what if, in the early universe, primordial black holes formed with just the right mass to be evaporating now? Their final moments could unleash a catastrophic burst of energy, a quantum-scale detonation visible across the cosmos as a fleeting radio flash. The idea isn't as far-fetched as it sounds. Primordial black holes, hypothetical relics from the universe's first seconds, have long been candidates for dark matter. If they exist, their evaporation could explain not just the Dragonfly, but other unexplained radio bursts lurking in telescope data. Yet skepticism remains. No one's ever detected Hawking radiation directly, let alone from a black hole small enough to explode. And without a second Dragonfly-like event to study, the theory remains just that, a tantalizing what-if scribbled at the edge of cosmology's playbook. For now, the Dragonfly burst remains an enigma, a solitary flash from the void that challenges our understanding of how energy moves through the universe. Whether it's the last gasp of a quantum black hole or something even more exotic, one thing's certain: the cosmos still holds phenomena that refuse to fit neatly into any textbook. And somewhere out there, in the darkness between galaxies, another dragonfly might be waiting to surprise us. Geminga should have been just another dead star, a silent, spinning corpse in the vast graveyard of the Milky Way. But when gamma-ray telescopes turned toward this pulsar 1,200 light-years away, they caught something extraordinary, a cosmic engine that refuses to run smoothly. Unlike the steady, metronomic pulses of most neutron stars, Geminga stutters. Its gamma-ray emissions hiccup unpredictably, surging and fading like a flickering streetlight in the cosmic dark. For astronomers, these uneven bursts aren't just quirks, they're clues that something fundamental is missing from our understanding of how these ultra-dense stellar remnants work. At first glance, Geminga fits the textbook definition of a pulsar. Born from a supernova explosion around 300,000 years ago, it's a neutron star spinning 4 times per second, its intense magnetic field funneling particles into beams of radiation that sweep past Earth like a lighthouse. But here's the twist: those beams should be the universe's most reliable clocks. The extreme physics of neutron stars, where matter is crushed into a sphere just 12 miles wide yet heavier than the Sun, creates conditions so stable that pulsars are used as interstellar timekeepers. Yet Geminga's timing is anything but precise. Its gamma-ray flashes arrive early or late by milliseconds, and their brightness varies wildly, as if something inside the star's ferociously magnetized crust keeps slipping out of sync. The leading suspect cracks in Geminga's magnetic armor. Neutron stars are thought to have rigid outer layers, crust so dense they're often compared to mountains of iron squeezed into a teaspoon. But simulations suggest that under the strain of immense magnetic forces, these crusts might fracture like tectonic plates, releasing bursts of energy that disrupt the star's emissions. Geminga's hiccups could be the seismic aftershocks of these cosmic quakes, reverberating through its magnetosphere. There's just one problem. No model fully explains why this pulsar's disruptions are so frequent, or why its gamma-ray flickers don't align with its X-ray pulses, a mismatch that defies current theories. That's where things get speculative. Some researchers propose that Geminga might be hiding a secret companion, a rogue planet or white dwarf orbiting just close enough to gravitationally tug on the star's crust, stirring up magnetic turbulence. Others wonder if we're seeing the effects of quantum weirdness at an unimaginable scale. In the core of a neutron star, protons and electrons are squeezed together so tightly they may form exotic states of matter, superfluid rivers or superconducting crystals that occasionally glitch, sending shockwaves through the star's structure. But the most tantalizing possibility is that Geminga isn't unique. It's just the first pulsar where we've noticed this behavior. As gamma-ray telescopes grow more sensitive, astronomers are finding other neutron stars with similar uneven pulses, hinting that our models of these cosmic powerhouses might need a radical rewrite. Whether it's hidden quakes, unseen companions, or physics we haven't yet imagined, Geminga's stuttering whispers remind us that even the universe's most predictable clocks can keep surprising secrets. And in those irregularities, we might just find the key to unlocking the true nature of matter at its most extreme. Before the wow signal, before fast radio bursts, there was the flicker that rewrote the rules. FRB 1919+21, the first pulsar ever detected. Discovered in 1967 by Jocelyn Bell Burnell, it earned the playful nickname LGM1, short for Little Green Men, because its rhythmic pulses were so precise they seemed artificially crafted. Every 1.337 seconds, like clockwork, a burst of radio waves swept past Earth, matching no known natural phenomenon. In that moment, the line between astrophysics and science fiction blurred. Could this be an alien beacon, a cosmic distress signal, or something even stranger? The truth turned out to be more astonishing than fiction. FRB 1919+21 wasn't a message from another civilization. it was the death throes of a star, collapsed into a spinning neutron star so dense it defied comprehension. This cosmic lighthouse, now known as the boomerang signal for its sweeping radio arcs, became the prototype for an entirely new class of celestial objects. Its discovery didn't just solve a mystery, it shattered assumptions. Suddenly, the universe revealed a phenomenon so precise it could rival human-made clocks, yet entirely natural. The little green men hypothesis faded, but in its place arose a deeper appreciation for the cosmos' ability to mimic and surpass our wildest imaginings. What makes the boomerang signal so revolutionary isn't just its history, but its legacy. Before pulsars, the search for extraterrestrial intelligence often fixated on artificial patterns, deliberate signals engineered to stand out. FRB 1919 plus 21 proved nature could produce rhythms just as exacting, forcing scientists to refine their criteria. If a spinning neutron star could impersonate an alien broadcast, how many other cosmic mimics were out there? The answer came swiftly. Over the next decades, hundreds of pulsars were catalogued, each with its own unique cadence, some even out-precisioning atomic clocks. Yet the boomerang signal still holds secrets. Unlike younger pulsars, it slowed considerably since its discovery, its once crisp pulses now slightly ragged with age. Some researchers speculate it might be veiled by a shroud of supernova debris, its light filtered through expanding shells of ancient star stuff. Others wonder if it hosts unseen planets, their gravity subtly warping its emissions. And then there's the lingering question that haunts all pulsar research: what happens inside these ultra-dense cores? At pressures where atoms collapse into seas of free quarks, the very laws of physics bend. The boomerang's steady ticks might be the closest we'll ever get to eavesdropping on quantum forces playing out on a stellar scale. Decades later, FRB 1919 plus 21 remains a cornerstone of astrophysics, a reminder that sometimes the universe's most astonishing signals aren't shouts from distant civilizations, but whispers from the depths of natural phenomena we're only beginning to understand. It taught us to listen more carefully, to question our assumptions, and above all, to expect the cosmos to surprise us. And in those lessons, the hunt for extraterrestrial intelligence didn't narrow, it deepened, armed with the knowledge that nature's wonders could be just as extraordinary as anything we might invent. Most of the universe is missing. That's the unsettling truth behind dark matter, the invisible, mysterious substance that outweighs all the stars, planets, and galaxies combined. We know it's there because of its gravitational pull, bending light and sculpting the cosmos. But what if dark matter isn't entirely silent? What if, somewhere in the void, it's whispering to us? That's the daring idea behind the dark matter radio hypothesis. The notion that when these elusive particles collide and annihilate, they might emit faint radio signals detectable across the universe. For decades, scientists have chased dark matter through indirect means, watching how it warps galaxies, how it shapes the cosmic web. But the dark matter radio hypothesis flips the script, proposing that dark matter might reveal itself not through gravity alone, but through subtle electromagnetic murmurs. The theory hinges on certain hypothetical dark matter particles, like WIMP weakly interacting massive particles, which could produce bursts of radio waves when they interact or decay. Picture two ghostly particles brushing against each other in the dark, their encounter sparking a fleeting burst of energy, a cosmic fingerprint lingering just long enough for our telescopes to catch. Hunting these signals is like listening for a pin dropping in a hurricane. Telescopes like LOFAR in the Netherlands and the Murchison Widefield Array in Australia scan the skies at ultra-low frequencies, sifting through the radio cacophony of pulsars, quasars, and human-made interference for anomalies that might betray dark matter's presence. One tantalizing candidate emerged from the center of our own galaxy, where an excess of unexplained radio waves, dubbed the WMAP haze, hints at something unusual. Could this be the radio echo of dark matter annihilations, a chorus of particles meeting their end in the Milky Way's crowded core? Skeptics point to simpler explanations: stellar winds, turbulent magnetic fields, or even undiscovered astrophysical phenomena. But supporters counter that the signal's distribution matches predictions for dark matter's expected density around the galactic center. It's a cosmic tug of war between caution and curiosity, where every new observation could tip the scales. Even if the current signals turn out to be false alarms, the search itself is reshaping how we look for the invisible. By tuning our instruments to the faintest frequencies, we're not just listening for dark matter, we're learning to hear the universe in a whole new way. The stakes couldn't be higher. If dark matter truly sings across the radio spectrum, it would be one of the most profound discoveries in science, a direct line to the universe's hidden architecture. And if not, the silence would be just as telling, forcing us to rethink what dark matter is and how it hides in plain sight. Either way, the hunt continues, with every faint signal a potential key to unlocking the cosmos' darkest secret. In October 2017, astronomers spotted something streaking through our solar system that didn't belong, a strange, tumbling object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout, it was the first confirmed visitor from interstellar space. But this wasn't just any rogue asteroid. Its bizarre properties ignited a firestorm of debate. Was it a chunk of cosmic debris or something far more intentional? The anomalies started stacking up. Oumuamua's shape defied nature's usual randomness, a cigar-like object possibly 10 times longer than it was wide, tumbling end over end like a flipped pencil. Most puzzling of all was its acceleration. As it hurtled away from the sun, it sped up slightly, as if pushed by an unseen force. Comets do this when their icy surfaces vaporize, creating a visible tail, but Oumuamua left no trail. Harvard astronomer Avi Loeb proposed a radical explanation. What if it wasn't being pushed by outgassing, but by sunlight itself? A solar sail, a thin, reflective structure used by theoretical spacecraft to harness radiation pressure, would behave exactly this way. The scientific backlash was swift. Critics argued Oumuamua's acceleration could be explained by exotic ices evaporating invisibly, or even by its unusual shape creating uneven thermal forces. But the real shock came when astronomers trained radio telescopes on the object, hoping to catch any artificial transmissions. Silence, no signals, no signs of technology. Just the empty crackle of space. To some, this was proof Oumuamua was just a weird rock. To others, it was even more suspicious. Why would an advanced probe announce itself? If it were alien, staying quiet would be the smartest move. The debate rages on because Oumuamua left before we could study it closely. By the time we noticed, it was already racing away at nearly 200,000 miles per hour. We'll never get another look. That's what makes this mystery so haunting. It slipped through our grasp, leaving behind just enough clues to tantalize us, but not enough to ever know for sure. Whether it was a cosmic oddball or a stealthy scout, Oumuamua taught us one thing: the universe is full of visitors. Next time, we'd better be ready. Among the wildest and most tantalizing theories about fast radio bursts is the idea that they might not be natural at all. What if, instead of cosmic accidents, some FRBs are deliberate markers, interstellar lighthouses, or even a galactic GPS system designed to guide travelers across the unimaginable distances between stars? It sounds like science fiction, but the concept isn't entirely frivolous. Consider the precision of some repeating bursts, their predictable timing, and their placement across the cosmos. If you were an advanced civilization trying to create a universal navigation grid, these fleeting but powerful signals would be an elegant solution. Mainstream astronomy, of course, leans toward less cinematic explanations. Magnetars, colliding neutron stars, and other high-energy astrophysical events can account for most FRB properties without invoking alien engineering. The sheer energy required to produce these bursts naturally exists in the universe, no cosmic cartographers needed. But the galactic GPS theory persists precisely because it highlights how little we truly understand. Take FRB 180916, the 16-day repeater. Its clockwork rhythm could easily be explained by a neutron star's orbit, or if you tilt your head, it could resemble a beacon cycling on and off to conserve power, waiting for someone to notice. The debate boils down to Occam's razor, the principle that the simplest explanation is usually the right one. For scientists, natural phenomena will always be the default assumption until evidence forces them elsewhere. Yet history shows that dismissing ideas too quickly can blind us to breakthroughs. Pulsars, after all, were initially mistaken for alien signals before their true nature was uncovered. The key is balance, entertaining radical possibilities while demanding rigorous proof. What makes the galactic GPS theory so compelling isn't its likelihood, but its audacity. It challenges us to rethink the boundaries of the possible. Even if every FRB turns out to have a mundane origin, the exercise of imagining alternatives sharpens our science. After all, the universe has surprised us before, and if there's one lesson from these mysterious signals, it's that the cosmos rarely follows our expectations. Whether they're natural or not, FRBs remind us that the universe is far stranger and far more inventive than we've yet dared to dream. After 24 signals that tease, mystify, and sometimes scream across the cosmos, we arrive at the most unsettling mystery of all: the silence. Not the crackle of static or the hiss of background radiation, but the deafening absence of what we expected to find, clear, undeniable proof that we're not alone. This is the silent sky paradox, the glaring contradiction at the heart of our search. With billions of galaxies, trillions of stars, and countless planets, why hasn't the universe shouted back? The numbers alone make the silence bewildering. Statistically, life should be everywhere. The Milky Way alone houses hundreds of billions of stars, many with planets in habitable zones. Even if only a fraction of those spawned intelligent civilizations, the cosmos should be buzzing with signals, deliberate broadcasts, accidental leaks, or the hum of interstellar infrastructure. Yet our telescopes hear nothing but the murmur of natural phenomena. This isn't just a puzzle, it's a cosmic cold shoulder. Scientists call it the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" The answers range from sobering to spine-chilling. Maybe civilizations are rare, snuffed out by cosmic disasters or their own self-destruction before they can reach the stars. Or perhaps they're deliberately hiding, observing us like a nature documentary while avoiding contamination. Some theorists suggest we're searching the wrong way, scanning for radio waves when advanced societies might communicate via neutrinos, quantum entanglement, or something we haven't even imagined. Then there's the darker possibility that something or someone enforces the silence. The Great Filter hypothesis warns that some catastrophic barrier prevents life from progressing beyond a certain point. If true, the filter could lie in our past, meaning we're miraculously lucky to exist at all. Or worse, it might await us in the future, a fate so inevitable that every civilization hits the same wall before reaching the stars. But here's the twist: silence isn't proof of absence. Our searches have barely scratched the surface. Imagine aliens scanning Earth 1,000 years ago. They'd have found no radio waves, no satellites, just quiet. We might be the cosmic equivalent of a quiet town before the invention of the telephone, oblivious to the chatter soon to come. Or maybe the signals are all around us, camouflaged as natural noise, waiting for the day we learn to listen properly. The silent sky paradox isn't an end, it's an invitation. Every mysterious signal we've explored hints at a universe far stranger, far more creative than we've dared to assume. The absence of answers doesn't mean we're alone. It means we're just beginning to ask the right questions. And somewhere in the quiet between the stars, the truth might be waiting for us to finally hear it. From the eerie precision of the wow signal to the rhythmic whispers of FRB 180916, each of these 25 cosmic enigmas peels back another layer of the universe's grand mystery. We've traced pulses from dying stars, decoded rogue radio bursts, and even dared to ask if some signals might bear the fingerprints of intelligence beyond Earth. Yet with every answer, the cosmos seems to toss another riddle our way. Take the dragonfly burst, a millisecond flash from nowhere, defying explanation, or the dark flow, where galaxies move in unison towards something beyond the edge of our sight. These aren't just anomalies, they're cosmic breadcrumbs, each one challenging what we thought we knew. What's striking isn't just the strangeness of these signals, but how they blur the line between nature's chaos and something almost intentional. The boomerang pulsar mimicked an alien beacon so perfectly it fooled its discoverers. The cosmic whistle chirps with a cadence that feels composed, not random. Even the vanishing stars of NGC 6946 leave behind X-rays that flicker like a malfunctioning switch. Are these mere quirks of physics, or could some even one be something more? Science demands skepticism, but it also thrives on imagination. The universe, after all, has no obligation to fit neatly into our textbooks. This search for meaning is humanity's oldest story. For millennia, we've looked to the stars and wondered who else might be watching back. Today, armed with telescopes and supercomputers, we're still asking the same question, just with better tools. The silent sky paradox reminds us how much we don't know, but it's not a verdict, it's an invitation. Every unexplained signal is a reminder that discovery doesn't end with what we've catalogued. It begins where our understanding falters, so keep listening, keep looking up, because somewhere out there, in the static between galaxies or the hum of a distant star, the next signal is waiting. And whether it's the cry of a magnetar or the hello we've always hoped for, one thing's certain: it'll rewrite the story we tell about our place in the cosmos. The universe isn't done surprising us. The only question is, will we be ready when it does?